Welcome back to the deep dive. So most of us use the internet all the time, right? But how it all actually works underneath, that's pretty much invisible. Today we're digging into a stack of sources that really break down the basics of how digital stuff talks to other digital stuff. Our goal, to make this whole hidden world of data flying around, well, visible. We're decoding networking fundamentals.
Yeah, and this is really key stuff. We're not just throwing terms around today. We want to explain the actual logic, how data gets reliably from, say, your phone across the world and back. If you can get your head around these core ideas, the addresses, the rules, how packets travel, then you'll really understand the engine driving, well, pretty much everything now.
Okay, let's start big picture then. Networking.
Mhm.
Fundamentally, it's just devices talking to each other, right?
Basically, yeah. Could be your laptop talking to your printer right beside it, or your phone hitting a server thousands of miles away.
But that communication happens on totally different scales. We
Yeah.
always hear these acronyms LAN, WAN, MAN. For someone listening who kind of gets the basics, how should they think about these different sizes?
Think of them like expanding circles, different scopes of connection. We can run through them pretty quick, smallest to biggest. So smallest scale, that's your PAN, personal area network. Think Bluetooth headset and your phone. Just a few feet, really.
Right, that one's easy, like my watch and phone syncing up.
Exactly. Step up from that, you get the LAN, local area network. That's your home Wi-Fi network. Or maybe your whole office building. It's where you share printers, files, that sort of thing locally.
Okay, got it. Home or office.
Go bigger again, and you hit the MAN, Metropolitan Area Network. Now you're talking connecting multiple LANs across maybe a city or a big university campus. Think city-wide fiber network some places have.
Right, connecting buildings or neighborhoods.
And then the big one, tying everything else together across countries, continents. That's the WAN, Wide Area Network. The internet itself is really the ultimate WAN, isn't it?
The WAN of WANs, yeah.
Exactly. But here's the interesting bit. It doesn't matter if it's a tiny pan or the global WAN. For a device to even participate, it needs the same basic foundational tools. And the biggest question right off the bat is about identity. How does a device get identified? Every single thing on a network needs two core identities. There's a physical one, and then there's a logical one.
Okay, that's a really key point. We hear about IP addresses all the time.
Yeah.
But you're saying there's also this other thing, a MAC address. Why two? Doesn't that seem kind of redundant?
It seems like it may be, but no, they do totally different jobs. So the physical identity, that comes from the actual hardware that connects you, the network interface card, or NIC, your Ethernet port, your Wi-Fi chip. Baked into that hardware permanently is a unique code. That's the M address, media access control address. Think of it like the device's serial number, fixed, doesn't change.
So the MSC address is only really useful right there in its immediate neighborhood, like just on my home Wi-Fi.
Precisely. It's how devices on the same local network segment find each other directly. Your router uses it to know exactly which computer or phone to send a particular piece of data to within your house. That MSC address, it never leaves your local network. It's strictly local.
Ah, okay. So when I want to talk to Google or something outside my house.
Then you need the other address, the logical one. That's the IP address, Internet Protocol address. This is more like your current mailing address. It can change, and crucially, it's routable. It lets data travel across different networks, hop from router to router all over the globe.
Okay, so MSC is the fingerprint on the hardware itself, stays local. IP is the address the network gives you, like a street address that lets data travel far and wide. And it can change, right? If I take my laptop to a coffee shop, it gets a new IP address.
Exactly. It gets a new logical address relevant to the network. And this IP address is super important. It's one of the 4 absolute must-haves for any device to be on a network. We've covered the NIC, which gives you the MAC address and the IP address. What else is needed?
All right, the 4 ingredients. What are the other 2?
You need the network media. That's just the path the data travels on. Could be copper Ethernet cables, could be Wi-Fi radio waves, could be fiber optic light pulses. The road basics.
Physical connection, okay.
And the last one, protocols, the rules of communication.
Okay.
Like TCP/IP.
Okay, hold on. If the IP address tells data where to go, why do we need these extra rules, these protocols like TCP/IP? Isn't the address enough?
Good question. Just having an address doesn't mean the message gets there reliably or even gets there at all. Protocols define how the conversation happens, and TCP/IP, well, that's actually 2 main protocols working hand in hand. IP, the Internet Protocol part, handles the basic addressing and routing. It's like putting the address on the envelope and getting it into the postal system, pointing it in the right general direction.
Okay, so IP is about the where. What about TCP then?
TCP, Transmission Control Protocol, that's the reliable part. See, IP on its own is what we call connectionless. It just sends the data pieces out and kind of hopes they arrive. That's effort.
Uh-oh. Doesn't sound very reliable for important stuff.
It isn't. That's where TCP comes in. TCP is like sending something via registered mail with tracking and delivery confirmation. It sets up a connection, numbers all the data packets, checks that they all arrive at the other end, puts them back in the correct order, and if any are missing or messed up, it asks for them to be sent again.
Ah, okay. So IP finds the city, TCP makes sure every single package gets delivered to the right house, intact, and assembled correctly.
That's a great way to put it. This split IP for addressing TCP for reliability is fundamental. It's what allows things like streaming video or online banking, where you absolutely cannot lose data or get it out of order, to actually work over the inherently messy internet.
Okay, this is making sense. We've got the different network sizes, the essential parts a device needs, NIC-AMP, IP, media, protocols, and the rules like TCP/IP. Now let's get to the really cool part. The actual journey. Walk us through it. What really happens step by step when I type, say, google.com into my browser and hit enter? Let's follow that request.
Right? The magic moment. This brings everything together.
Yeah.
First thing, your computer doesn't know where google.com is in terms of an IP address. It only knows the name. So it needs to translate that friendly name into the numerical IP address Google servers actually use. To do that, it asks the DNS, the domain name system. Think of it as the internet's giant distributed phone book.
So it shouts out, hey DNS, what's the number for google.com?
Pretty much. Your computer sends a query to a DNS server, which might ask other DNS servers, until it finds the current IP address for google.com. Let's say it comes back with 142.250.190.78.
Okay, now my computer has the number.
Now it crafts the actual request. Like, please send me the main web page. This request data gets chopped up into small, standardized chunks. These are the packets. Every single packet gets wrapped up. Think of it like a tiny digital envelope. It gets stamped with a destination IP address, 142.250.190.78, and also your computer's source IP address, so Google knows where to send the reply.
Okay, packet's ready to go, addressed and everything. But wait a sec. My computer inside my house probably has an IP address, like 192.168.1 something, right? A private address. That address doesn't work out on the public internet, does it?
Excellent catch. Exactly right. Those 192.168 or 10 addresses are private. They're meant only for local use inside your LAN. They aren't routable on the global internet. This is where things get a little more complex and where probably the most important device on your network steps in, your default gateway. Usually that's your home router.
The box my ISP gave me, or the one I bought?
That router does something really clever called NAT, Network Address Translation.
Okay, let's pause there. NAT, why is that needed? What does it actually do?
NAT is basically a workaround. We ran out of the original style of public IP addresses, IPv4, ages ago. There just aren't enough unique public addresses for every single device in the world. So NAT lets whole networks of devices inside your home or office share a single public IP address, the one assigned to your router by your internet service provider. When your packet, with its private source IP, 192.168.1.0, say, hits the router on its way out, the router performs NAT. It strips off that private source IP address and replaces it with its own public IP address. Then it sends the packet out to the internet.
Just like the router is acting as a gatekeeper, putting its own return address on all the mail going out from inside the house.
Precisely. And it keeps a little table internally. It remembers, okay, that request that just went out using my public IP address going to Google, that actually came from the computer at 192.168.1.10 inside.
So when Google sends the web page back,
the response packets come back addressed to your router's public IP. The router gets them, looks at its NAT table, sees, this reply is for the conversation started by 192.168.1.16 hour, translates the destination IP back to your computer's private IP, and forwards the packet directly to your machine on the local network using its MMAS address.
Wow, okay. That NAT step is crucial. It's hiding my whole internal network behind one address.
It is. It was essential for scaling the internet. Now, think about troubleshooting for a second. If your Wi-Fi feels sluggish.
Yeah, happens all the time.
Understanding these pieces helps. Is it the media? Like, is your Wi-Fi signal just weak where you are? Or is it maybe a protocol issue? Maybe there's tons of network congestion, packets are getting lost, and TCP is having to resend things over and over, slowing everything down.
Or maybe I can't connect at all.
Right. If you can't even get an IP address, the problem might be with your NIC, or maybe the DHCP service on the router that hands out IPs isn't working. If you have an IP but can't reach the internet, Maybe the default gateway setting is wrong, or the router itself is having trouble with NAT or talking to the ISP.
Okay, yeah, knowing the ingredients helps pinpoint where the failure might be. That makes sense. So back to the journey. The packet left my router, now wearing the router's public IP address. It's out on the big internet, the WAN. What happens next?
Now it really starts traveling. It leaves your local ISP's network and hits the wider internet backbone. That packet is going to hop between many different powerful routers, big industrial strength ones. Each router looks at the destination IP address stamped on the packet, 142.250.190.78 for Google. It consults its massive internal map of the internet, its routing table, and decides which connection is the best next hop to get that packet closer to Google's servers. Then it forwards it.
And this happens again and again. Hop, hop, hop.
Yep, dozens of times, potentially. Across different networks owned by different companies, maybe across undersea cables, these routers are constantly talking to each other, updating their maps based on traffic, link failures. It's called dynamic routing. They're always trying to find the most efficient path right now.
So it's not like a fixed train track. It's more like finding the best roads based on current traffic jams.
Exactly. It might travel thousands of miles, bounce through multiple data centers. Finally, after all those hops, it arrives at a router connected to Google's data center network. That router knows the final destination IP is inside its network, and it delivers the packet to the specific Google web server.
And then Google sends the web page back.
Right. The server processes your request, send homepage. It generates the HTML, images, etc., breaks that down into response packets, stamps those with your router's public IP as the destination, and sends them back out onto the internet. Those packets then make their own journey, hopping router to router, potentially taking a different path than you're requested, until they arrive back at your router.
Where the router does the NAT magic again, checks its table, swaps the public IP for my computer's private IP, and sends it to my machine using the MSE address.
And your browser gets the packets, TCP puts them all back in the right order, reassembles the web page, and boom, Google appears on your screen, all in, like a fraction of a second.
That is incredibly complex, but it works billions of times a second all over the world.
It's an amazing feat of engineering and standardization. Every single click, every video frame, every text message, it's all broken down into these little packets, each addressed and sent on its way, relying on this whole system of addresses and protocols.
So, okay, we've traced the big journey, but does networking always have to involve the internet, routers, NAT, all that complexity? What about just connecting two computers directly?
Absolutely not. The most basic network possible strips away almost all that complexity. You can connect just two PCs together. That's a peer-to-peer network. Maybe back in the day you wanted to copy a bunch of files or play a game directly with a friend. You could just run an Ethernet cable between two computers.
Ah, yeah, the crossover cable days.
Right. Or even with modern Ethernet. But the key thing there is there's no router automatically handing out IP addresses using DHCP. You have to do it manually.
So you'd have to go into the network settings on each computer.
Exactly. You take the two computers, let's call them PC0 and PC1, connect them with that cable. Then you go into PC0 settings and manually type in an IP address, maybe 192.168.1.1, and you'd also set its subnet mask, usually 255.255.255.1. Then you go to PC1 and give it a different address in the same range, like 192.168.1.2 with the same subnet mask. Now they're logically in the same neighborhood.
And how do you know if it worked?
The classic test, the ping command. From PC0, you'd open a command prompt and type ping 192.168.1.2.
And if you get replies back?
Success. You've established basic network communication. They can talk. That simple setup really demonstrates the core. You need the physical connection, the media, the cable, and you need compatible logical addresses, IP addresses, in the same network range. The NICs are doing their job with MASI addresses locally, and you're using the basic IP protocol. It's networking at its simplest.
Okay, that really grounds it. So let's recap the journey we took today. We started with the different scales, PAN, LAN, MAN, WAN, from your smartwatch to the entire internet.
Right. Then we hit the core identity crisis, the difference between the physical, local MAC address tied to the NIC and the logical, routable, potentially changing IP address.
And the four essential ingredients for any network device. The NIC providing the MP, the IP address, the physical network media, and the crucial protocols like TCP/IP that define the rules of reliable communication.
We spent a good chunk following that data packet journey, DNS lookup, packet creation, the critical role of NAT at the default gateway or router, hopping across the internet, and the return trip.
Showing how every single thing we do online is basically Millions of tiny addressed packets flying around.
Exactly. So we now have a pretty good picture of what travels the packets. We know where they travel across these different network scales, and we understand the addressing IP and MA that guides them. But there's another layer, isn't there? How is all this data actually prepared? How does your browser know how to package a web request versus how an email client packages an email? How does the data get structured before it even becomes an IP packet?
Right. There must be some kind of standard way to organize all these different tasks, from the application down to the physical wire. A blueprint.
There is. Think about it. If every packet is like a letter with an address, imagine the sheer complexity of the global postal system needed to handle billions of them every second, perfectly reliably. What kind of universal standards, what meticulous layered rules must be in place to manage that potential chaos? To make sure the software at the top can talk seamlessly to the hardware at the bottom, and everything in between.
That sounds like a system with many layers of responsibility.
Precisely. And that structural challenge, that need for a standardized blueprint, that's exactly what the OSI model, the Open Systems Interconnection model, was designed to solve. And that's where we'll dive in next time.